Hello everyone, let's continue with elementary number theory. Today we'll study how to solve linear congruence. A linear congruence in general looks like this. AX is congruent to B mod M. This expression is called a congruence. Since X has degree 1, it's called linear congruence. This expression is called congruence. Since X has degree 1, it's called a linear congruence. Let's look at a very special case first. Very special case. If A equal to 1, then we have X congruent to B mod M. Very special case. A equal to 1. If A equal to 1, then we have X congruent to B mod M. So keep the rule in mind. The rule to solve linear congruence is we try to get X by itself on the left side. We try to get S by itself on the left side. On the right side, the number on the right side, it must be the least non-negative residue of M. On the left side, we must get X by itself. On the right side, the number here on the right side must be the least non-negative residue of M. Let's look at some very simple example first. Solve X. X congruent to 18 mod 7. Solve X. X congruent to 18 mod 7. So on the left side, we already get S by itself. On the left side, we already get S by itself, so that's fine. On the right side, this number must be the least non-negative residue mod 7. Here 18 is more than 7. So 18 is more than 7 is not the least non-negative residue. So we take 18 divided by 7. Take 18 divided by 7, take remainder. 18 divided by 7, remainder is 4. Divided by 7, remainder is 4. And 4 is less than 7. So this is the least non-negative residue mod 7. So this is the solution. X is congruent to 4 mod 7. Or we can write it as an equation. We can write X equal to 4 plus 7t, where t is an integer. We can write it as a congruence, or we can write the answer as an equation. S equal to 4 plus 7t, where t is an integer. There are two ways to write the answer. X congruent to 125 mod 13. X congruent to 125 mod 13. When we solve congruence, on the left side, we must get X by itself, which we already have X by itself. So left side is okay. On the right side, this number here, it must be a least non-negative residue mod 13. Here 125 is more than 13, so that's not the least non-negative residue. We take 125 divided by 13 and take remainder. Take 135 divided by 13 and take remainder. 125 divided by 13. 13 goes into 125 9 times. 9 times 13 is 117. When I subtract, remainder is A. So that means 125 congruent to A mod 13. 125 congruent to A mod 13. Here number A is less than 13. So that's the least non-negative residue mod 13. So we can leave The answer is x congruent to a minus 13. Or we can write it as an equation. We can write x equal to a plus 13t, where t is an integer. Either way is okay. Next, x congruent to negative 62 minus 9. X congruent to negative 62 minus 9. 62 by itself is more than 9. If we ignore negative sign here, 62 by itself is more than 9. We first of all take remainder. Remember, we cannot divide negative number to take remainder. Let's divide positive 62 first. Positive 62 divided by 9. We take positive 62 divided by 9. Remainder is a. That means 62 congruent to a minus 9. Therefore, if I multiply both sides by negative 1, negative 62 congruent to negative a minus 9. So negative 62 congruent to negative a minus 9. Negative 62 congruent to negative a minus 9. But we want the least non-negative residue. This number is negative. Here I can add 9. Since we are doing mod 9 here, I can add 9 here. Add 9. Negative a plus 9 is 1. So x congruent to 1 minus 9. This number 1 is less than 9. So that's the least non-negative residue minus 9. We can write different answer like this. S congruent to 1 minus 9. Or we can write it as an equation. S equal to 1 plus 9t, where t is an integer. Next example. S congruent to negative 78 mod 22. X congruent to negative 78 mod 22. Well, this number is negative, and 78 itself is more than 22. 78 itself is more than 22. So take 78, divide by 22, take remainder. Remember, we cannot divide negative number to take remainder. Let's divide positive 78 and take remainder. Positive 78 divided by 22. We know that 22 goes into 78 3 times. 3 times 22 is 6. 66. 78 minus 66 is 12. That means 78 congruent to 12 mod 22. 78 congruent to 12 mod 22. So negative 78 congruent to negative 12 mod 22. So here, negative 78 congruent to negative 12 mod 22. But for the number here, we need to find the least non-negative residue here. This number is not negative, it's positive. So this number is not positive, it's negative here. We try to make it non-negative, so I can add 22 here. For congruence, I can add any multiple of 22 to either side. Here, let me add 22 here. Negative 12 plus 22 is positive 10. So S congruent to 10 mod 22. Here 10 is less than 22. Here 10 is less than negative 22. So 10 is the least non-negative residue of 22. That's the final answer. Or we can write x equal to 10 plus 22t, where t is an integer. So keep the rule in mind. When solving congruence, for the final answer, x has to be isolated. isolate means get x by itself. We need to get x by itself. X must be isolated on the left side. X must be isolated on the left side of the congruence. X must be isolated on the left side of the congruence. And the number on the right side must be a least non-negative residue ma M. Least non-negative residue ma M. So we must get x by itself on the left side. The number on the right side, it must be a least non-negative residue ma M. Least non-negative residue means it must be greater than or equal to 0, and it must be less than M. 4 must be less than 7. 8 must be less than 13. 1 must be less than 9. Here 10 must be less than 22. And it must be non-negative. It must be non-negative. Next, let me show you the general case of linear congruence. General linear congruence. In general, the linear congruence looks like this. AX congruent to B ma M. Where A, X, B, M, they are all integers. A, X, B, M, they are all integers. And M must be positive. In a special case, A is 1. In a special case, we consider A equal to 1. But in general, A is not 1. In general, we have AX congruent to B ma M. That's called a general linear congruence. In order to solve for X, we'll discuss this problem in 3 cases. In order to solve for X, I'll discuss this problem in 3 cases. So, let's first of all take GCD. First of all, take GCD for AM. If GCD equal to 1, I'll consider this as case 1. If GCD of AM equal to 1, I consider this as case 1. Now, if GCD of AM is not 1, if the GCD of AM equal to D, which is not 1, I divide this into 2 small cases. If the GCD of AM equal to D, which is not 1, I divide this into 2 cases. I take D divides B. Take D divides B. If D divides B, if B is divisible by D, if B is divisible by the GCD, that means D divides B. I take this as case 2. When GCD of AM equal to D and D divides B, I take this as case 2. Case 3, if D doesn't divide B, D either divides B or it doesn't divide B, I take this as case 3. I will discuss this problem in these 3 cases. Case 1, case 2, case 3. Let's look at case 1 first. Case 1. The GCD of AM equal to 1. If the GCD of AM equal to 1, then by a theorem we learned earlier, we know that inverse of A ma M exists. If GCD of AM is equal to 1, then by a theorem we learned earlier, we know that inverse of A ma M exists. then inverse of A mod M exists. I can multiply both sides of the congruence. By inverse of A. I can multiply both sides of the congruence by inverse of A. If I multiply both sides of the congruence by inverse of A, on the left side, A will cancel negative A. Will cancel inverse of A. On the left side, A will cancel inverse of A. We get S by itself on the left side. So, let's look at some simple examples here. Solve for X. 7X congruent to 4 mod 19. 7S congruent to 4 mod 19. Keep in mind, be very, very careful. Inverse of A is not 1 over A. Inverse of A is not 1 over A. Everything here must be integers. Everything here must be integers. Inverse of A is not 1 over A. We cannot multiply both sides by 1 over 7 to cancel X. We cannot multiply both sides by 1 over 7 to cancel 7. Inverse of A is not 1 over A. Be very, very careful. Inverse of A is not 1 over A. Be very, very careful. Everything here must be integers, must be whole numbers. Keep it in mind, inverse of A is not 1 over A. So in this linear congruence, 7 represents A, 4 represents B, 19 represents M. That's A, B, M. A, B, M. 7 represents A, 4 represents B, 19 represents M. First step, let's check GCD of AM. What's the GCD of AM here? GCD of 7 and 19 is what? GCD of 7 and 19 is 1. So that's in case 1. We know that inverse of A mod M exists. So we know that inverse of 7 mod 19 exists. Inverse of 7 mod 19 exists. How do we find inverse of 7 mod 19? In order to find inverse of 7 mod 19, we try to find some integer times 7 plus some integer times 19 equal to 1. We try to find some integer times 7 plus some integer times 19 equal to 1. If we can find such integers here, then the number in front of 7, the number in front of 7 is the inverse of 7 mod 19. If I can find integers times 7 plus integer times 19 equal to 1, then the integer in front of 7 is the inverse of 7. And for inverse of 7 mod 19, an earlier example, for inverse of 7 mod 19, inverse of 7 mod 19, in the earlier example, inverse of 7 mod 19, we found it is 11. Inverse of 7 mod 19, we found it is 11. We found that using extended Euclidean algorithm, we find that 1 equal to 3 times 19 minus 8 times 7. The number in front of 7 is negative 8. The number in front of 7 is negative 8. So inverse of 7 congruent to negative 8 mod 19. In general, try to use the least non-negative residue. So I add 19 here. Negative 8 plus 19 is 11. So inverse of 7 is 11. According to the earlier example, we know that negative 8 plus 3, negative 8 times 7 plus 3 times 19 equal to 1 by using extended Euclidean algorithm. That's what we did earlier. Then here we know that the number in front of 7, the number in front of 7 is the inverse of 7. So inverse of 7 congruent to negative 8 mod 19. In general, we try to use the least non-negative residue here. So I can add 19 here. This number is negative. In order to make it positive, I can add 19 here. Negative 8 plus 19 is 11. So by the earlier example, we know that inverse 7 congruent to 11 mod 19. inverse of 7 congruent to 11 mod 19. So inverse of 7 congruent to 11 mod 19. Inverse of 7 congruent to 11 mod 19. On the left side, if I multiply, 7 times inverse of 7, they get cancelled because it's congruent to 1. 7 times inverse 7 congruent to 1. So they get cancelled. We get 1x. 7 times inverse of 7 is congruent to 1. We get x, 1x. Here on the left side, I get s by itself. On the right side, 4 times 11 is 44. Mod 19. For the final answer, we must have x on the left side. And the number on the right side, it must be the least non-negative residue mod 19. Since 44 is more than 19, it's not the least non-negative residue. Since 44 is more than 19, it's not the least non-negative residue. In order to find the least non-negative residue, take 44 divided by 19 and take the remainder. 44 divided by 19. 19 goes into 44 two times. 2 times 19 is 38. 44 minus 38, remainder is 6. So x congruent to 6 mod 19. That's the answer for x. Or sometimes we can write it as an equation. We can write x equal to 6 plus 19t, where t is an integer. Next example, solve for x. 13x congruent to 5 mod 61. 13x congruent to 5 mod 61. So first step, let's check GCD of 13 and 61. In case 1, the GCD of AM must be 1. If GCD of AM is not 1, we must consider case 2 and case 3, which I'll show you later. So let's first of all check GCD of 13 and 61. GCD of 13 and 61. If I calculate correctly, it should be 1. GCD of 13 and 61, since they are both prime numbers. Since both 13 and 61 they are prime numbers, their GCD must be 1. So it satisfies the condition in case 1. We can apply in the first case. We can apply case 1. Then since GCD of 13 and 61 is 1, that means I can find inverse of 13 mod 61. Since their GCD is 1, that means I can find the inverse of 13 mod 61. How do we find inverse of 13 mod 61? In order to find inverse of 13 mod 61, we try to find some integer times 13 plus some integer times 61 that congruent to 1. We try to find some integer times 13 plus some integer times 61 that equal to 1. Here we can use the extended Euclidean algorithm. And by example we did earlier, here we use extended Euclidean algorithm. We get 1 equal to 3 times 61. 1 equal to 3 times 61 minus 14 times 13. So the coefficient of 13 is negative 14. Coefficient of 61 is number 3. By example we did earlier, we know that negative 14 times 13 plus 3 times 61 equal to 1. By earlier example, we know that 1 equal to 3 times 61 plus negative 14 times 13. So we know that negative 14 times 13 plus 3 times 61 equal to 1, which means the inverse of 13 is a number in front of 13, which is negative 14 mod 61. So inverse of 13 is negative 14 mod 61. In general, we try to use the least non-negative residue here. So I can add 61 to this number. I get 47. That means inverse of 13 congruent to 47 mod 61. Inverse of 13 congruent to 47 mod 61. Be very, very careful. Inverse of 13 is not 1 over 13. Everything here must be whole number. Inverse of 13 is not 1 over 13. Be very, very careful. Inverse 13 is not 1 over 13. General, inverse of 8 is not 1 over 8. Be very, very careful. So, multiply both sides by inverse of 13. Inverse of 13 congruent to 47 minus 61. If I multiply on the left side, 13 and inverse 13 get cancelled because they congruent to 1. 13 and inverse 13 they congruent to 1, they get cancelled. 1 times x is x. On the right side, 5 times 47 is 235. Mod 61. Then here on the left side I get s by itself. On the right side, make sure this number, it must be in the least non-negative residue. It must be the least non-negative residue mod 61. Since 235 is more than 61, we must take a remainder. Do division, take remainder. 235 divided by 61. 61 goes into 35 3 times. 3 times 61 is 183. If I subtract, I get 52. So the remainder is 52 when I divide. Now 52 is positive, it's non-negative, and it's less than 61. So this is a least non-negative residue mod 61. I can leave the answer the way it is. On the left side, I get s by itself. On the right side, it's a number, which is the least non-negative residue mod 61. Or we can write the answer as an equation. S equal to 52 plus 61t, where t is an integer. We can write the congruence as an equation. Next example. 34x congruent to 3 mod 9. Next, 34x congruent to 3 mod 9. First step, let's verify. This is A, this is B, this is M. Let's verify. What's the GCD of A and M? In order to use case 1, GCD of AM must be 1. What's the GCD of AM? 34 may be too big here. 34 may be too big here. This 34 may be too big here. So we can try one thing. We know that for linear congruence, I'm allowed to add and subtract any multiple of 9 on either side. For linear congruence, I'm allowed to add or subtract any multiples of 9 to either side. Here, 34 is more than 9. If I subtract 27x, 27x is a multiple of 9. If I subtract 27x on left side, this congruence stays the same. I get 7x congruent to 3 mod 9. I can make the congruence easier. The number gets smaller now. For congruence, I'm allowed to add or subtract any multiples of 9, of m on either side. I'm allowed to add or subtract any multiples of m on either side. Here I can subtract 27x on the left side, because 27x is a multiple of 9. X is an integer. 27x is a multiple of 9. So I can subtract 9 on both sides. I get 7x. I get 7x on the left side. That's congruent to 3 mod 9. So a simpler way to get 7, a quicker way to get 7 is I take 34 divided by 9, take remainder. A quicker way is take 34 divided by 9, take remainder. That's a quicker way to get 7. So a quicker way is I can take 34 divided by 9 and then take remainder. So this congruence can be rewritten as 7x congruent to 3 mod 9. If a number is more than 9, it's more than m, I can take this number divided by m and take remainder. So this linear congruence can be simplified as 7x congruent to 3 mod 9. Next, let's verify the GCD. What's the GCD of 7 and 9? GCD of 7 and 9 is 1. Therefore, I can find the inverse of 7 mod 9. I can find the inverse of 7 mod 9. How do we find inverse of 7 mod 9? We try to find some number times 7 plus some number times 9 that equal to 1. It must be whole numbers. We try to find some whole numbers that multiply by 7 plus some whole numbers that multiply by 9 equal to 1. Once I find the integers, the number in front of 7, the number in front of 7 is the inverse of 7 mod 9. Now, for small numbers, we can try it out. For small numbers, we can try it out. When numbers are small, we can try and get an answer. But when the number is very, very large, if we can't guess, we must use the extended Euclidean algorithm. When the numbers are small, we can try and get an answer. We can get an answer by trial and error. That's okay. But when the numbers are large, we must use the extended Euclidean algorithm. So can we guess two integers here to make something times 7 plus something times 9 equal to 1? We know that 5 times 7, here I get number 5 by guessing. 5 times 7 is 35. 4 times 9 is 36. If I take negative 35 plus 36, I'll get 1. We know that 5 times 7 is 35, 4 times 9 is 36. If I take negative 35 plus positive 36, I get 1 here. Once I find integers here, that means inverse of 7 is a number in front of 7, it's a coefficient of 7. The inverse of 7 is a coefficient of 7. So inverse of 7 congruent to negative 5 mod m. M is 9. Inverse of 7 congruent to negative 5 mod 9. Now this number is negative. In order to make non-negative residue, I can add 9 here. Negative 5 plus 9 is 4. So inverse of 7 congruent to 4 mod 9. Inverse of 7 congruent to 4 mod 9. If I multiply left side to the left side, right side to the right side, on the left side, number 7 times inverse of 7, they congruent to 1, we get 1x. 1x is the same as x. On the right side, 3 times 4 is 12. Then 12 divided by 9. 12 is more than 9 here. 12 divided by 9, remainder is 3. Because this number must be least non-negative residue, it must be positive, it must be non-negative, it must be less than 9. So that's the answer. S congruent to 3 mod 9. S congruent to 3 mod 9. Or we can write the answer as the equation. S equal to 3 plus 9t, where t is an integer. S equal to 3 plus 9t, where t is an integer. Next example. 295x congruent to 4 mod 27. So we can see that this number is very big. It's much larger than m. I can take this number, divide by m, and take remainder. I can take this number, divide by m, and take remainder to make it a little easier. 295 divided by 27. 27 goes to 29 one time. Remainder is 25. 27 goes to 25 0 times. So remainder is 25. 295 divided by 27, remainder is 25. That means 295x congruent to 25x. 295x congruent to 25x, because remainder of 295 divided by 27 is 25. 295 congruent to 25 mod 27. That means 295x congruent to 25x mod 27. 295 congruent to 25 mod 27. If I multiply both sides by x, 295x congruent to 25x mod 27. So 295x congruent to 25x mod 27. Number 4 stays the same. If I simplify this linear congruence, I can make it much easier. This number is much smaller than 295. Next, let's check the GCD. Let's check the GCD for A and M. These three numbers they represent A, B, M. Check the GCD for A and M. GCD of 24 and 27. The only common factor is 1. So GCD of 24 and 27 is 1. Next, we try to find inverse of 25 mod 27. Next, we try to find the inverse of 25 mod 27. In order to find inverse of 25, we try to find some number times 25 plus some number times 27 that equal to 1. In order to find the inverse of 25 mod 27, I try to find some integer times 25 plus some integer times 27 that equal to 1. When the numbers are big, it's not easy to guess. When the numbers are big, it's not easy to guess. If we can guess, we must use the extended Euclidean algorithm. If we can guess here, we must use the extended Euclidean algorithm. So let's use extended Euclidean algorithm. Let's first of all apply Euclidean algorithm to find the GCD. GCD of 24 and 27. We take larger number divided by smaller number. 27 divided by 25. 25 goes to 27 one time. 1 times 25 is 25. Remainder is 2. Then replace the larger number with a remainder. Then take 25 divided by 2. Take remainder. 25 divided by 2. 2 goes to 25 12 times. 12 times 2 is 24. Remainder is 1. Remainder is 1. Replace the larger number with a remainder. Replace the larger number with a remainder. Then take larger number divided by smaller number. 2 divided by 1. We know that 1 goes into 2 times. 2 times 1 is 2. Remainder is 0. Remainder is 0. Replace the larger number with a remainder. GCD of 1 and 0 is 1. That's the same as what we have here. Next, we try to write 1 in terms of 24 and 27 with integer coefficients. Here we use the extended Euclidean algorithm. First of all, convert each division into equations. First division here, 27 equal to 1 times 25 plus 2. 27 equal to 1 times 25 plus 2. Second division, 25 equal to 12 times 2 plus 1. 25 equal to 12 times 2 plus 1. In the third division, number 2 equal to 2 times 1 plus 0. So we can first of all cross out the last row, which ends with a 0. Then for the rest, get a remainder by itself. For the rest of the rows, get a remainder by itself. In the last row here, 1 equal to 25 minus 12 times 2. 2 equal to 27 minus 1 times 25. Now we try to substitute. Start from the last equation. We try to substitute. Last equation says 1 equal to 25 minus 12 times 2. Last equation says 1 equal to 25 minus 12 times 2. I can replace number 2 with the previous row. So 1 equal to 25 minus 12 times 2. 2 is 27 minus 1 times 25. 2 is 27 minus 1 times 25. Then distribute 12. I have 12 times 27. Double negative is positive. Plus 12 times 25. We have 25 here. Plus 12 25. Together is 13 25. Minus 12 27. If I combine that, I have 13 25 minus 12 times 27. So the coefficient in front of 12, the coefficient in front of 25 is 13. Coefficient in front of 27 is negative 12. So since 13 times 25 plus negative 12 times 27 equal to 1, I plug in 13 here, plug in negative 12 here. Since 13 times 25 plus negative 12 times 27 is 1, the number in front of 25 is the inverse of 25. So inverse of 25 congruent to 13 mod 27. Next, once I know inverse of 25, I multiply both sides by inverse of 25. Inverse of 25 congruent to 13 mod 27. If I multiply on the left side, 25 times inverse 25, that's 1. 1x is the same as x. So 25 can cancel. On the right side, 4 times 13 is 52. Mod 27. Here on the left side, we get s by itself. On the right side, 52 is more than 27. So we must take a remainder. Find the least non-negative residue. Take a remainder. Find the least non-negative residue. 52 divided by 27, remainder is 25. Mod 27. So that's an answer. S congruent to 25 mod 27. Or we can write it as an equation. Or we can write it as an equation. S equal to 25 plus 27t, where t can be any integer. That's an answer here. But now, how do we check an answer? How do we check an answer? In order to check an answer, we plug in 25 for x. Plug in 25 for x. Take 295 times 25. Take 295 times 25. Then divide by 27. If the remainder is 4, that means we get the right answer. Plug in 25 for x. Take 295 times 25. Then divide by 27. If the remainder is 4, then we get the same answer. That means we get the correct answer. So let's check an answer. If we want to check an answer, plug in 25 for x. Plug in 25 for x. 295 times 25. Here I use my calculator. 295 times 25. I get 7,375. 295 times 25. I use my calculator. I get 7,375. Then I take this number. Take 7,375 divided by 27. If the remainder is 4, that means we get the right answer. If the remainder is 4, that means we get the right answer. Let's divide. 7375 divided by 27. 27 goes into 73 2 times. 2 times 27 is 54. 73 minus 54 is 19. Carry 7 down. 27 goes into 197 7 times. 7 times 7 is 49. 2 times 7 is 14. 14 plus 4 is 18. So check. 197 minus 189 is A. 27 goes into 85 3 times. 3 times 27 is 81. Remainder is 4. Remainder is 4. That means this number congruent to 4 mod 27. Get the same answer. The answer is correct. This answer is correct. That's how we check the answer. If we plug in 25, then multiply and divide by 27. If the remainder is 4, that means we get the right answer. That's how we check the answer. Next, let's discuss case 2. How do we solve the general linear congruence in case 2 when the GCD of AM is D, which is not 1, and D divides B? How do we solve the linear congruence in case 2? So, for case 2, before we discuss case 2, let me show you two theorems first. Case 2, GCD of AM is D, which is not 1, and D divides B. Before we discuss case 2, let me show you two theorems first. Those are two small theorems, it's called lemma. Let me show you two lemmas first. First lemma. Let A and B be integers. And let D be the greatest common divisor of A and B. Then the GCD of A over D and B over D equal to 1. First lemma, let A and B be integers, and let D be the greatest common divisor of A and B. Then the GCD of A over D and B over D is 1. This theorem says, this lemma says, if D is the greatest common divisor, I take A divided by D, B divided by D. The greatest common divisor of A over D and B over D must be 1. How do we prove it? So, let's prove it. We try to prove that the GCD of A over D and B over D is 1. So, let the GCD of A over D and B over D be E. I try to show E is 1. Let the GCD of A over D and B over D be E. Then E must be greater or equal to 1. The greatest common divisor must be greater than or equal to 1. The greatest common divisor must be greater than or equal to 1. Next. Then here we know that since E is the greatest common divisor of A over D and B over D, then E divides A over D and E divides B over D. Since E is the greatest common divisor, then E divides both numbers. E divides A over D and E divides B over D. Then E divides A over D, that means E times the integer K equal to A over D, and E times the integer L equal to B over D. If E divides A over D, that means E times the integer equal to A over D. If E divides B over D, that means E times the integer L equal to B over D, where K and L are integers. Then, if I multiply in both equations, if I multiply both sides by D, I have E dk equal to A and E dl equal to B. If I multiply both sides by D, I have E dk equal to A, E dl equal to B. Put E and D together. Let's put E and D together. Consider this is one number. Consider E times D is one integer. If this number times the integer equal to A, if this number times the integer equal to A, that means this number divides A. if this number times the integer equal to a, that means this number divides a. If this number times the integer equal to b, that means this number divides b. So ed divides a and ed divides b. If ed divides a and ed divides b, then ed must be a common divisor of ab. So e times d is a common divisor of a and b. So since ed divides a, ed divides b, ed is a common divisor of a and b. ed is a common divisor of a and b. Since ed divides a, ed divides b, ed must be a common divisor of a and b. But here, d is the greatest common divisor. D is the greatest common divisor of AB. Since D is the greatest common divisor of AB, then D must be greater than every common divisor. Since D is the greatest common divisor, D must be greater than every common divisor. Then I can say D is greater than ED. Since this is a common divisor, D is the greatest common divisor, so D is greater than ED. If I divide both sides by D, since D cannot be 0, common divisor cannot be 0. If I divide both sides by D, I have 1 is greater than or equal to E. If I divide both sides by D, I have 1 is greater than or equal to E. Hence, E is less or equal to 1. Since E is greater than or equal to 1 and less than or equal to 1, E must be 1. Since E is greater than or equal to 1 and E is less than or equal to 1, E must be 1. If E is greater than or equal to 1 and E is less than or equal to 1, E must be 1. If E is greater than or equal to 1 and E is less than or equal to 1, E by itself must be 1. So, E must be 1. Hence, the GCD of AD over BD must be 1. Hence, the GCD of A over D, comma, B over D must be 1, since E is 1. The greatest common divisor of A over D and B over D must be 1. Let's complete the proof of this lemma. Next lemma, let AX, BM be integers with m greater than 0, and let D equal to GCD of AM. If D divides B, and AX congruent to B mod M, then A over D times X congruent to B over D mod M over D. So we'll try to prove this. Let's prove it. First of all, we try to show that A over D, B over D, M over D, they are all integers. Since D is the GCD of AM, then we know that D divides A and D divides M. Now we can say A over D and M over D, they are both integers. Since D divides A, D divides M, then A over D and M over D, they are both integers. Since D divides B, then B over D is also integer. It's also integer. Since D divides B, then B over D is also integer. Next, start from here. Since AX congruent to B mod M, that means M divides AX minus B. AX congruent to B mod M means M divides AX minus B. Then, so I can say mk equal to ax minus b, where k is an integer. Next, I can divide, this is the equation, I can divide both sides by d. Since d is the GCD, it cannot be 0. D is the GCD of am, d cannot be 0. So I can divide both sides of the equation by d. If I divide left side by d, I get m over d times k. If I divide the right side by d, I have a over d times x minus b over d. If I divide both sides by d, I have m over d times k equal to a over d times x minus b over d. Then we write it back in this form. Then consider this is one integer. Consider this is one integer. Integer times integer minus integer is integer. Consider this is one integer. This is also integer. If this number times the integer k equal to another integer, if this number times the integer k equal to this number, that means m over d divides a over dx minus b over d. So if this number times the integer k equal to another integer, I can say this integer divides the bigger integer here. So m over d divides a dx minus b over d. Then I can say a over dx by definition of congruence. A over dx congruent to b over d mod m over d. So a over dx congruent to b over d mod m over d. They look like fractions, but they're all integers. They look like fractions, but they're all integers. They're all integers. So let's complete the proof of this lemma. Now, based on these two lemmas, what can we say about the case 2? What can we say about the case 2? The linear congruence is ax congruent to b mod m. Based on these two lemma, what can we say about case 2? Let's call this lemma 1. Call this lemma 2. Based on these two lemma, what can we say about case 2? In case 2, we have D is the GCD of AM. D is the GCD of AM, and D divides B. So it satisfies the hypothesis of the second lemma. D is the GCD of AM, and D divides B. It satisfies the hypothesis of lemma 2. Then, according to lemma 2, I can divide ADM by D. I can divide ABM by D. I can divide each of ABM by D. So in case 2, if GCD of AM is D, which is not 1, and D divides B, we can divide by lemma 2, we can divide each of A, B, M by d. We can divide each of a, b, m by d. Then we have a new congruence. Then we have a new congruence. A over d x congruent to b over d mod m over d. Here, since d is the greatest common divisor of am, so a over d is an integer. M over d is also integer. And since d divides b, so b over d is also integer. They are all integers here. And also, by first lemma, if d is the GCD of two numbers, a and b, when I divide both numbers by d, their GCD will be 1. Since d is the GCD of am, then if I divide a by d and divide m by d, their GCD will be 1. By the first lemma, since d is the GCD of am, if I take both numbers divided by d, then their GCD will be 1. That's first lemma. If d is the GCD of two numbers, if I take both numbers divided by d, then their GCD will be 1. Here, since d is the GCD of am, if I take both numbers divided by d, their GCD will be 1. Now look at this new congruence here. Consider this, there are 3 integers here. If I treat a over d as a prime, if I treat b over d as b prime, if I treat m over d as m prime, then here, I treat a over d as a prime, I treat m over d as m prime. Then this linear congruence looks like case 1. It looks like a case 1 linear congruence. It's in the form of a prime x congruent to b prime by m prime, such that the GCD of a prime and m prime is 1. It satisfies all conditions in case 1. We can follow case 1 to solve this linear congruence. It satisfies all conditions in case 1. A prime x congruent to b prime by m prime, and the GCD of a prime and m prime is 1. It satisfies all necessary conditions in case 1. We can apply case 1 to solve this new linear congruence. Let me rewrite case 2 over. When we are solving general linear congruence, AX congruent to B by M, if GCD of AM is D, which is not 1, and D divides B, divide each of A, B, M by D. Divide each of A, B, M by D. Then we have A over D, B over D, and M over D here. And the GCD of A over D, the first number, and the last number is 1. The GCD of A over D and M over D is 1. Then it satisfies all necessary conditions in case 1. We follow case 1 to solve for x. Let me show you an example. Here. Solve for x. (27x) congruent to 24. Mod 48. 27x congruent to 24 mod 48. First of all, let's observe the GCD of A and M. These 3 numbers represent A, B, and M. First of all, let's observe the GCD of A and M. The GCD of 27 and 48. GCD of 27 and 48 is what? 27 is 3 times 9. 9 is 3 times 3. So 27 is 3 to the power of 3. That's the prime factorization of 27. 48 can be written as 3 times 16. 16 is 4 times 4. 4 is 2 times 2. So the prime factorization for 48 is 2 to the power 4 times 3 to the power 1. Then for the greatest common factor, 27 can be written as 2 to the power 0 times 3 to the power 3. 48 is 2 to the power 4 times 3 to the power 1. Choose a lower power. For GCD, choose a lower power. We have 2 to the power 0 times 3 to the power 1, which is 3. So the GCD of 27 and 48 is 3. Now, we check if D divides B. This is D. This is D. Let's check if D divides B. Does 3 divide 24? Does 3 divide 24? We know that 3 times 8 is 24. 3 times 8 is 24, so 3 divides 24. 3 times 8 is 24, so 3 divides 24. So we have GCD equal to 3, which is not 1. But 3 divides 24. Then follow case rule. Follow the rule of case 2. Follow the rule of case 2. We divide each of A, B, M by D. Divide each A, B, M by the GCD. Divide all three numbers by the GCD. We have 9x congruent to A mass 16. We have 9x congruent to A mass 16, and we know that the GCD of 9 and 16, the GCD of A over D, M over D is always 1. GCD of 9 and 16 is 1. Next, from the rule in case 1, we try to find the inverse of 9 mass 16. We try to find the inverse of 9 mass 16. Once I find inverse of 9, I multiply both sides by inverse of 9. I can cancel x here. I can cancel 9 here, get s by itself. Now, find inverse of 9. Can we find some integer that times 9 plus some integer times 16 that equal to 1? Can we find some integer that times 9 plus some integer times 16 that equal to 1? For small numbers, we can try it out. But for large number, we need to use extended Euclidean algorithm. Here, can we try it out? We know that 9 times 9 is 81. 5 times 16 is 80. 9 times 9 is 81. 5 times 16 is 80. If I use 81 minus 80, I can get 1. So I can put 9 here, put negative 5 here. 9 times 9 is 81. And negative 5 times 16 is negative 80. 81 plus negative 80 is positive 1. Since 9 times 9 plus negative 5 times 16 equal to 1, the number in front of 9, is inverse of 9. So inverse of 9 congruent to 9 mass 16. So inverse of 9 congruent to 9 mass 16. Now if you can get this number, you must use extended Euclidean algorithm. If you can't get this number by trial and error, you must use extended Euclidean algorithm. Then here we find inverse of 9 by trial and error, which is 9, which is number in front of 9. Then I multiply both sides by inverse of 9. if I multiply both sides by inverse of 9, inverse of 9 congruent to 9 minus 16. On the left side, number 9 inverse of 9 get cancelled, we get s by itself. On the right side, 8 times 9 is 72 minus 16. Then 72 is larger than 16. We need to put the least non-negative residue here. Since 72 is larger than 16, we take 72 divided by 16 and take remainder. 72 divided by 16, remainder is 8. So that's an answer. S congruent to A minus 16. Or we can write S equal to A plus 16t, where t is an integer. Either way is okay. We can write x congruent to a minus 16, or I can write x equal to a plus 16t, where t is an integer. Next example, 34x congruent to 6 minus 72. 34x congruent to 6 minus 72. First step, we check the GCD of A and M. We check the GCD of A and M. These three numbers represent A, B, M. These three numbers represent A, B, M. We must match this equation, A, B, M. First step, find GCD of A and M. Here A is 34, M is 72. What's the GCD here? We can use we can use prime factorization. We can use prime factorization to find the GCD. 34 is 2 times 17. They are both primes. So there's 2 to the power 1 times 17 to the power 1. How about 72? 72 is 8 times 9. A is 4 times 2. 4 is 2 times 2. 9 is 3 times 3. So 72 can be written as 2 to the power 3 times 3 to the power of 3 to the power of 2. Then we try to find the GCD. For 34, I can write it as 2 to the power 1. If there's no 3, we write 3 to the power of 0 times 17 to the power of 1. For 72, we have 2 to the power 3 times 3 to the power of 2 times, since there's no 17, write 17 to the power of 0. Then for the GCD, we choose the lowest power. 2 to the power of 1, 3 to the power of 0, 17 to the power of 0. If we multiply, I get 2. So the GCD of 34 and 72 is 2. Since the GCD is 2, let's check. If 2 divides middle number, we can apply the rule in case 2. If 2 divides the middle number, if the GCD divides the middle number, we can use the rule in case 2. And we know that 2 divides 6, because 2 times 3 is 6. 2 divides 6. So we can use the rule in case 2. Here, the GCD of 34 and 72 is 2. And 2 divides 6. Then I can divide every number by 2. I take 34 divided by 2. 6 divided by 2. And 72 divided by 2. I have 72x. So I have 17x congruent to 3 minus 36. And we know that by the previous theorem, we know that the GCD of 17 and 36 must be 1. GCD of 17 and 36 must be 1. Then I can find the inverse of 17. Then I can find the inverse of 17 and multiply inverse of 17 on both sides and get s by itself. Now, how do we find inverse of 17 minus 36? We try to find some integer times 17 plus some integer times 36 that equal to 1. It looks not easier here. It's hard to get a number. It looks not easier. If we can guess these two numbers, we must use the extended Euclidean algorithm. If we can guess these two integers, we must use the extended Euclidean algorithm. If we can guess, that's fine. In the previous problem, if we can guess, that's fine. But if we cannot guess for large numbers, if we are not able to guess, we must use the extended Euclidean algorithm. So first of all, let's try to find the GCD of 17 and 36. Thirty-six divided by 17. Seventeen goes to 36 two times. 2 times 17 is 34. Remainder is 2. Replace the larger number of the remainder. Then take 17 divided by 2 for the remainder. 17 divided by 2. 2 goes to 17 8 times. 8 times 2 is 16. Remainder is 1. Replace the larger number of the remainder. Then take the larger number divided by the smaller number. 2 divided by 1. 1 goes to 2 2 times. 2 times 1 is 2. Remainder is 0. Replace the larger number of the remainder. GCD of 1 and 0 is 0, is 1. Next, rewrite each division as an equation. Rewrite each division as an equation. First division, 36 equal to 2 times 17 plus 2. 2 times 17 plus 2. Next division, 17 equal to a times 2 plus 1. Last equation, 2 equal to 2 times 1 plus 0. We cross out the last row which ends with a 0. Cross out the last row which ends with a 0. Then for the other rows, get a remainder by itself. Get a remainder by itself. Here I have 1 equal to 17 minus a times 2. In the first row, I have 2 equal to 36 minus 2 times 17. Then substitute. I have 1 equal to 17 minus a times 2. I can replace 2 with the previous row. I can replace number 2 with the previous row. So 1 equal to 17 minus a times 36 minus 2 times 17. Distribute a, I get negative a times 36 plus 16 times 17. If I combine like terms, 117 plus 1617 will be 1717. 1 plus 16 is 17. That's 17 times 17 minus a times 36. And since I find two integers such that integer times 17 plus integer times 36 is 1, the number in front of 17 is the inverse of 17. The number in front of 17 is the inverse of 17. Here the number in front of 17 is 17 itself. So inverse of 17 is 17 itself. Inverse of 17 congruent to 17 plus 36. So inverse of 17 congruent to 17 plus 36. Then once I find the inverse of 17, I multiply both sides by inverse of 17. Multiply both sides by inverse of 17. Inverse of 17 congruent to 17 plus 36. If I multiply left side to the left side, right side to the right side, 17 times inverse of 17 get cancelled. We get s by itself. 3 times 17 is 51. Plus 36. 51 is more than 36, so I take remainder. 51 divided by 76. Remainder is 15. So s congruent to 15 plus 36. X congruent to 15 plus 36. That's the answer. or we can write x equal to 15 plus 36t, where t is an integer. That's the final answer. Either this or this. That's the final answer. Next, let's discuss case 3. If the GCD of AM equal to D, which is not 1, and D doesn't divide B, how do we solve this linear congruence? If GCD of AM is not 1, and D doesn't divide B, the GCD doesn't divide the middle number, how do we solve this linear congruence? Case 3. If the GCD of AM equal to D, which is not 1, and D doesn't divide B, how do we solve this linear congruence? AX congruent to B by M. How do we solve it? Claim there's no solution. In this situation, there are no solution. If the GCD of AM is D, which is not 1, if the GCD of AM is not 1, and D doesn't divide B, there are no solutions. Then there are no solutions. To this linear congruence, AX congruent to B by M. How do we prove it? How do we prove there's no solution? How do we prove there's no solution? We can try to prove by contradiction. In order to show there's no solution to this linear congruence, we try to prove by contradiction. Prove by contradiction. Assume there is a solution to this linear congruence. Assume there is a solution X, then X must satisfy this congruence. Then X is an integer, and AX congruent to B map M. A solution X must satisfy this congruence. Then, by definition of congruence, AX congruent to B map M, that means M divides AX minus B. Hence, M times the integer K equal to AX minus B, where K is an integer. So, if I get B by itself, in this equation, I have B equal to AX minus MK. If I get B by itself, B equal to AX minus MK. Next, we know that GCD of AM is D. Since D is the GCD of AM, then D divides A and D divides M. Since D is the GCD of AM, then D divides both A and M. If D divides A, D divides M, then D divides any linear combination of AM. Since D divides A, D divides M, D divides any linear combination of AM. D divides any linear combination of AM. Here X is an integer. K is also an integer. So D divides any linear combination of AM with integer coefficients. X is integer, K is also integer. And we know that this is B. AX minus MK is B. So D divides B. But in the assumption we say that D doesn't divide B. In the assumption we say that D doesn't divide B. So that's a contradiction. That's a contradiction here. This is contradiction. So this is a contradiction. Once we find contradiction, that means our assumption was wrong. There does not exist any solution. There does not exist any solution. So there are no solutions. To this linear congruence, AX congruent to B, my M. Next, let's do a simple example. Solve for X. If I give you 15X congruent to 4 minus 35. If I give you 15X congruent to 4 minus 35, how do we solve for X? We first of all check GCD for AM. GCD of 15 and 35 is 5. And we know that 5 doesn't divide 4. This 5 doesn't divide the middle number. 5 doesn't divide 4. So there are no solutions. We first of all find the GCD of AM. If GCD divides the middle number, then we divide all three numbers by the GCD. And then follow case 1. Follow the step in case 1. If the GCD doesn't divide the middle number, then there are no solution. Here, let me write all three cases over. When we solve linear congruence in the form of AS congruent to B my M, we first of all find the GCD of AM. If case 1, if the GCD of AM is 1, then we can find inverse of A my M. Then multiply both sides by inverse of A and solve for X. That's case 1. Case 2, if the GCD of AM equal to D, which is not 1. If the GCD of AM is D, which is not 1, and then if D divides B, if D divides the middle number, then we divide all three numbers ABM, divide ABM by D. Then we have a new linear congruence. Solve it in the same way as in case 1. It's case 2. If the GCD of AM is D and D divides the middle number, that's the case 2. We divide all three numbers ABM by D. That's case 2. Case 3. If the GCD of AM is D, which is not 1, and D doesn't divide B. If the GCD of AM is not 1, it's D, which is not 1, and D doesn't divide the middle number, then there are no solutions. Next, let me show you how to solve for a system of linear congruence. 7x congruent 15 minus 16, and 4x congruent to 7 minus 13. If there are two linear congruences, we solve one of them first, and then substitute the answer into the other one. So here we have two linear congruences. Solve for one of them, and then substitute the answer into the other one. Which one should we solve first? In general, I suggest you solve the one that has larger modulus first. Solve the one that has larger modulus first. So 16 is larger than 13. Solve the one that has larger modular first. So solve the first equation first. 7x congruent to 15 minus 16. So first of all, check GCD. GCD of 7 and 16 is 1. So I can find inverse of 7 minus 16. Find inverse of 7 minus 16. Can we try to find some number that times 7 congruent plus some number times 16 that equal to 1? Can we find some number that times 7 plus some number times 16 that equal to 1? If we can try it out, that's good. But if we cannot find such number, we must use the extended Euclidean algorithm. Here, let's try. If I take 3 times 16, we have 48. If I take 7 times 7, I have 49. We know that 49 minus 48 is 1. So I put negative 3 here. 49 plus negative 48 is 1. 49 plus negative 48 is 1. So once I can find such integers, the number in front of 7 is the inverse of 7 minus 16. So number in front of 7 is the inverse of 7 minus 16. So the inverse of 7 congruent to 7 minus 16. Then multiply both sides by inverse of 7. Inverse of 7 congruent to 7 minus 16. When we multiply 7 and inverse of 7 can cancel. We have 1. 7 times inverse 7 congruent to 1. 1 times x is x. 15 times 7 is 105. Then 105 is more than 16. We take 105, divide by 16 and take the remainder. Take 105, divide by 16 and take the remainder. 105 divided by 16. 16 goes into 105 6 times. 6 times 16 is 96. Remainder is 9. So x congruent to 9 minus 16. So x congruent to 9 minus 16. Next, try to write this as an equation, then substitute into the other linear congruence. Try to write this as an equation first. X congruent to 9 minus 16 means x equal to 9 plus 16t, where t is the integer. X congruent to 9 minus 16 means x equal to 9 plus 16t, where t is the integer. So that's the solution to the first linear congruence. Next, I substitute this solution into the second linear congruence. If I substitute, I have 4 times 9 plus 16t congruent to 7 minus 13. If I substitute, I replace this x. I replace this x with 9 plus 16t. Replace this x with 9 plus 16t. Then, if I distribute 4, I have 36 plus 64t congruent to 7 minus 13. 36 plus 64t congruent to 7 minus 13. 36 is more than 13. I can try to take remainder. 36 is more than 13. I can try to take remainder. 36 divided by 13, remainder is 10. 36 divided by 13, remainder is 10. 64 is also more than 13. I can take remainder. 64 divided by 13. Remainder is 12. Then I can subtract 10 from both sides. I have 12t congruent to negative 3 minus 13. I can subtract 10 from both sides. 12t congruent to negative 3 minus 13. In general, we want to make this number positive, so I can add 13 here, make it positive. We try to make this number positive, so I can add 13 here, make it positive. So 12t congruent to 10 minus 13. That's another linear congruence. That's A, B, M. Next, try to find the GCD of AM. GCD of AM is 1. GCD of 12 and 13 is 1. If the GCD is 1, that means we can find the inverse of 12 minus 13. Can we try it out? Can we find some number times 12 plus some number times 13 equal to 1? That's easy. Negative 1 times 12 plus positive 1 times 13. Negative 1 times 12 plus positive 1 times 13 is 1. So the inverse of 12 is negative 1. The number in front of 12 is inverse of 12. In general, try to use positive numbers, so I can add 13 here. Inverse of 12 congruent to 12 minus 13. Inverse of 12 congruent to 12 minus 13. Then multiply both sides by inverse of 12. If I multiply both sides by inverse of 12, 12 and inverse of 12 get cancelled. I get t by itself. 10 times 12 is 120 minus 13. 120 is more than 13. We try to find the least non-negative residue. 120 is more than 13. So take 120 divided by 13, take remainder. 120 divided by 13, take remainder. 13 goes into 120 9 times. 9 times 13 is 117. Remainder is 3. So t congruent to 3 minus 13. Now be very, very careful. This is not the answer. We are solving for x. This is t. This is not the answer. We are not done. We are solving for x. This is t. We are not done. How do we solve for x? Write t as an equation. Write the linear congruence as an equation first. This can be rewritten as t equal to 3 plus 13. Don't use t again. Use a different letter. Three plus 13, say u, where u is an integer. Then I can substitute this t here and find new x. Substitute this t here, find new x. If I substitute t here, I have x equal to 9 plus 16 times t. T is 3 plus 13u. If I distribute 16, I have 9 plus 48. 16 times 13, that's 208. Then 9 plus 48 is 57 plus 208u. So the final answer, right, x equal to 57 plus 208u. U is an integer. That's one way to not answer. X equal to 57 plus 208u. U is an integer. Or we can write it as a linear congruence. Or I can write x congruent to 57 mod 208. That's another way to write an answer. We can write it as an equation x equal to 57 plus 208u, where u is an integer. Or I can write x congruent to 57 mod 208. Either way is okay. Next example, 5x congruent to 7 mod 24. 11x congruent to 1 mod 18. This is a system of linear congruence. Solve one of them first, then substitute the answer into the other one and solve for the final answer. So usually we start from the one that has larger modular. Here 24 is larger than 18, so I start from the first linear congruence. Usually start from the one that has larger modular, which will have less computation at the end. 4x congruent to 7 mod 24. So first of all, check GCD of AM. That's A, B, C. Check GCD of AM. GCD of 5 and 24 is 1. That means we can find the inverse of 5 mod 24. Can we find some number times 5 plus some number times 24 that equal to 1? Can we find some integer times 5 plus some integer times 24 that equal to 1? We can try 5. 5 times 5 is 25. And we know 25 minus 24 is 1. 25 minus 24 is 1. Once I can find integers, make some integer times 5 plus some integer times 24 equal to 1. The number in front of 5 is the inverse of 5. The number in front of 5 is the inverse of 5. So the inverse of 5 congruent to 5 mod 24. Then I multiply both sides by inverse of 5. Inverse of 5 congruent to 5 mod 24. If I multiply, on the left side, 5 and inverse of 5 can cancel, it can add by itself. On the right side, 7 times 5 is 35. So x congruent to 35 mod 24. Since 35 is more than 24, we can take 35 divided by 24 and take the remainder. 35 divided by 24 is the remainder is 11. So x congruent to 11 mod 24. Next, write this as an equation, then substitute into the other equation, into the other linear congruence. If I write it as an equation, s equal to 11 plus 24t, where t is an integer. Then I can substitute this x into the other linear congruence. If I substitute x here, I have 11 times 11 plus 24t congruent to 1 mod 18. Distribute 11. 11 times 11 is 121. 11 times 24 is 264 times t congruent to 1 mod 18. Next, we see that here 121 is more than 18. 264 is also more than 18. We need to take a remainder. Since both numbers are more than 18, we need to take a remainder. 121 divided by 18. 18 goes to 121. Let's try 6, see if it works. Let's try 6. 6 times 18 is 108. 121 take away 108 is 13. The remainder is 13. 121 divided by 18, remainder is 13. So 121 congruent to 13. 264 divided by 18. 18 goes in 26 one time. Remainder is 8 and 4. 18 goes into 84. 18 goes into 84. 4 times 18 is 72. Subtract, remainder is 12. So 264 congruent to 12 mod 18. Next, I can subtract 13 from both sides. 12d congruent to negative 12 mod 18. 12t congruent to negative 12 mod 18. In general, we want positive number here. We don't want negative 12 here. We try to make it positive. So I can add 18 here. If I add 18, I have 12t congruent to 6 by 18. Now this is a linear congruence. Next, we try to find the GCD of A and M. These three numbers, they are A, B, M. Next, try to find GCD of A, M. GCD of 12 and 18 is 6. And we know that 6 divides 6. 6 divides 6. This 6 divides the other 6. So since 6 divides the middle number, that's case 2, I can divide all three numbers here by 6. We can divide all three numbers A, B, M by 6. Divide all three numbers A, B, M by 6. If I divide all three numbers by 6, I have 2t congruent to 1 mod 3. We have 2t. If I divide all three numbers by 6, I have 2t congruent to 1 mod 3. Now the GCD of 2 and 3 is 1. I can find the inverse of 2 mod 3. We can find the inverse of 2 mod 3. Let's guess. Can we find some number times 2 plus some number times 3 equal to 1? Let's try negative 1 and positive 1. We know that negative 1 times 2 is negative 2. Negative 2 plus 3 is positive 1. So the number in front of 2 is the inverse of 2. Inverse of 2 congruent to negative 1 mod 3. Inverse of 2 congruent to negative 1 mod 3. In general, we try to use positive numbers. So I can add 3 here. Inverse of 2 congruent to 2 mod 3. Inverse of 2 congruent to 2 mod 3. Here I multiply both sides by inverse of 2. If I multiply 2 and inverse of 2 can cancel, we get t by itself. On the right side, 1 times 2 is 2. So t congruent to 2 mod 3. But be very, very careful, we are not done. We are solving for x. We are solving for x. And we found t here. We are not done. We are solving for x. Then we need to write this linear congruence as an equation. Get t by itself. Then substitute t here and find x. If I write this as an equation, I write t equal to 2 plus 3. Don't use t. Use a different letter. T equal to 2 plus 3u, where u is an integer. Then I can substitute t here. Substitute t here, get x by itself. If I substitute t, I have x equal to 11 plus 24 times t, where t is 2 plus 3u. If I distribute 24, I have 11 plus 48 plus 72u. Combine like terms, 11 plus 48 is 59. 59 plus 72u. So for the final answer, we can write x equal to 59 plus 72u, where u is an integer. That's one way to write the answer. That's one way. That's okay. That's one way. Another way is we can write this as a linear congruence. We can write this as a congruence. Write x congruent to 59 mod 72. Either way is okay. X congruent to 59 mod 72. X congruent to 59 mod 72. How do we check the answer? How do we check the answer? If we want to check the answer, this number 72 here, 72, it must be the least common multiple of 24 and 18. This number here, it must be the least common multiple of 24 and 18. And for 59 here, 59 must be the least non-negative residue of 72. This number must be less than 72. This number here, it must be less than 72, strictly less than 72. And if I plug in 59 for x, it must satisfy both equations. That means if I plug in 59 here, take 5 times 59, then divide by 24, the remainder must be 7. If I plug in 59 here, 11 times 59, if I divide by 18, the remainder must be 1. So check three things. this number, the modular must be the least common multiple of both 24 and 18. The number in the from, it must be less than 72. The number in the from here, it must be less than 72. And if I plug in the number, it must satisfy both linear congruence. Next example, S congruent to 1 must 6, S congruent to 2 must 7, and S congruent to 3 must 11. So if there are 3 linear congruents doing the same thing, solve one of them first, substitute the answer into the second one, solve the second one, and then substitute the answer into the third one, solve the final answer. Solve for the final answer. So usually we start from the one that has the largest modular. Start from the one that has the largest modular. Let me start from the last one first. So last one says x congruent to 3 by 11. That means x equal to 3 plus 11t, where t can be any integer. That's the solution to the third linear congruence. Then we substitute the answer into the second largest modular, into the linear congruence with the second largest modular, which is the second one. Substitute x here. If I substitute, I have 3 plus 11t. 3 plus 11t congruent to 2 must 7. Now, try to solve for t. Here, 11 is more than t. 11 is more than t. I can take 11 divided by 7 and find the remainder. 11 divided by 7, remainder is 4. So the left side can be rewritten as 3 plus 4t congruent to 2 must 7. 3 plus 4t congruent to 2 must 7. Next, I can subtract 3 from both sides. So 4t congruent to -1 must 7. In general, we don't want negative number here. So I can add 7 here. Add 7 to -1. -1 plus 7 is +6. So 4t congruent to +6 must 7. Next, let's check. This is a linear congruence. The three numbers here are A, B, and C. Let's check GCD of A, M. Sorry, these three numbers are A, B, and M. Let's check GCD between A and M. GCD of 4 and 7 is 1. So that means I can find the inverse of 4 must 7. Can we find some integer that times 4 plus some integer times 7 that equal to 1? We know that 2 times 4 is A. A minus 7 is 1. So 2 times 4 plus -4 times 7 is 1. Once I can find integers, make the integer times 4 plus integer times 7 equal to 1. The number in front of 4 is the inverse of 4. So inverse of 4 congruent to 2 must 7. Inverse of 4 congruent to 2 must 7. Then multiply both sides by inverse of 4. Then if I multiply, 4 times inverse of 4 can cancel with the t by itself. On the right side, 6 times 2 is 12. And here, 12 is more than 7. So I can take 12 divided by 7, take the remainder. 12 divided by 7, remainder is 5. So t congruent to 5 must 7. Next, we try to write this as an equation. T equal to 5 plus 7 is a different letter u. T equal to 5 plus 7u, where u is an integer. Then we substitute t into the first equation, but in the first equation there's no t. We try to substitute t into the first equation, but in the first equation there's no t. That means I need to substitute t here. Find x first, then substitute x into the first equation. So substitute t here, find x. If I substitute t here, I have x equal to 3 plus 11t, and t is 5 plus 7u. Then simplify, get x by itself. If I distribute 11, I get 55 plus 77u. 3 plus 54 is 58 plus 77u. That's x. Next, I can substitute x into the first equation. Next, I can substitute this x into the first equation. If I substitute x, I have 58 plus 77u congruent to 1 mod 6. If I substitute x here, I have 58 plus 77u congruent to 1 mod 6. Then both 58 and 77, they are larger than 6. I can take both numbers, divide by 6, and take remainder. 58 divided by 6. 6 goes to 58 9 times. 9 times 6 is 54. Remainder is 4. So 58 congruent to 4 mod 6. Next, take 77 divided by 6. 6 goes to 17 twice. 2 times 16. 2 times 6 is 12. Remainder is 5. So 77 congruent to 5 mod 6. Next, I can subtract 4 from both sides. If I subtract 4 from both sides, 5u congruent to negative 3 mod 6. In general, we try to make this number positive, so I can take negative 3 plus 6. Negative 3 plus 6 is positive 3. So I got 5u congruent to 3 mod 6. Now, this is a linear congruence. The three numbers here are a, b, and m. A, b, and m. Check GCD for a and m. GCD of 5 and 6 is 1. That means I can find the inverse of 5 mod 6. Can we find some integers? Let times 5 plus integer times 6 equal to 1. Can we guess some number here? Some integer times 5 plus integer times 6 equal to 1. We can try negative 1 and positive 1. Negative 1 times 5 is negative 5. Negative 5 plus 6 is positive 1. So the number in front of 5 is the inverse of 5. Inverse of 5 congruent to negative 1 mod 6. In general, we prefer positive numbers. So I add 6 here. If I add 6 here, negative 1 plus 6 is 5. So inverse of 5 congruent to 5 mod 6. Inverse of 5 congruent to 5 mod 6. Then multiply both sides by inverse of 5. Inverse of 5 congruent to 5 mod 6. If I multiply on the left side, 5 times inverse of 5 can cancel, you get u by itself. On the right side, 3 times 5 is 15. So u congruent to 15 mod 6. But 15 is more than 6. If you're going to find the least non-negative residue, take 15 divided by 6, take the remainder. So the least non-negative residue is 3. 15 divided by 6, remainder is 3. u concurrent to 3 minus 6. Here we have u concurrent to 3 minus 6. That means u equal to 3 plus 6v, where v is an integer. Use different letters. U equal to 3 plus 6v, where v is an integer. And since we are solving for x, I substitute this u here. I can find x. Substitute u here. I can find x. S equal to 58 plus 77u. Replace u with 3 plus 6v. (77 times 3 is 231. 77 times 6 is 462. Combine like terms. 58 plus 231 is 289 plus 462v. So for the final answer, we can write S equal to 289 plus 462v. Where v is an integer. That's one way to learn answer. Or we can use congruence. We can write x congruent to 289 mod 462. Either way is okay. We can write it as an equation or write it as a linear congruence. Next example, S congruent to 1 mod A, S congruent to 9 mod 13, and S congruent to 3 mod 30. So usually we start from the one that has largest modular. Here the largest modular is 30. Start from the one that has largest modular. So start from last one. S congruent to 3 mod 30. Write that as an equation. That means S equal to 3 plus 30t, where t is an integer. So S equal to 3 plus 30t, where t is an integer. Then substitute the answer into the second largest modular. The second largest is 13. So substitute this x here. We have 3 plus 30t congruent to 9 mod 13. 3 plus 30t congruent to 9 mod 13. Here 30 is more than 13. 30 is more than 13, so I can take 30 divided by 13 and take remainder. 30 divided by 13, remainder is 4. So we get 3 plus 4t congruent to 9 mod 13. Then I can subtract 3 from both sides. I have 4t congruent to 6 mod 13. This is a linear congruence. The three numbers here, a, b, and m. Check GCD for a and m. GCD of 4 and 13 is 1. That means I can find the inverse of 4 mod 13. Can we find some number that times 4 plus some number times 13 that equal to 1? Can we find some integer that congruent that times 4 plus a number times 13 equal to 1? We know that 3 times 4 is 12. And 13 minus 12 is 1. So I can make negative 3 here, positive 1 here. Negative 3 times 4 is negative 12. 1 times 13 is 13. 13 minus 12 is 1. Once I can find integers, then make the integer times 4 plus integer times 13 equal to 1. The number in front of 4 is the inverse of 4. So inverse of 4 congruent to negative 3 mod 13. inverse of 4 congruent to negative 3 minus 13. In general, we try to make this number positive. In general, try to use positive number here. So I can add 13 here. I can add 13 here. If I add 13 here, I get inverse of 4 congruent to 10 minus 13. So inverse of 4 is 10. Next, I can multiply both sides by inverse of 4. Next, I multiply both sides by inverse of 4. Inverse of 4 congruent to 10 minus 13. When I multiply, 4 times inverse of 4 can cancel, I get t by itself. 6 times 10 is 60. Since 60 is more than 13, I want to find the least non-negative residue. 60 divided by 13, the remainder is 60 divided by 13. 13 goes into 60 4 times. 4 times 13 is 52, remainder is A. So 60 divided by 13, remainder is A. That means t congruent to A minus 13. That means t congruent to A minus 13. Next, we try to write t as an equation. Write t as an equation. I can write t equal to A plus 13 is a different letter called u, where u is an integer. So t equal to A plus 13u, where u is an integer. Then I need to substitute t here for a new x, and then substitute x into the first linear congruence. Plug in t here for a new x, then plug x into the first linear congruence. I have x equal to 3 plus 30t. T is A plus 13u. Then distribute 30. S equal to 3 plus 240 plus 390 u. Combine like terms. S equal to 243 plus 390 u. Next, I substitute x into the first linear congruence. Substitute x into the first congruence here. If I substitute, I have 243 plus 390u congruent to 1 mark A. 243 is more than A. 390 is more than A. So I take both number divided by A, take remainder. 243 divided by A goes to 24 3 times. 3 times A is 24. Bring 3 down. A goes to 3 0 times. 0 times A is 0. Remainder is 3. Take 390 divided by A. A goes to 39 4 times. 4 times A is 32. 39 minus 32 is 7. Bring 0 down. A goes to 70 8 times. 8 times A is 64. Remainder is 6. So 390 divided by A, remainder is 6. 243 divided by A, remainder is 3. I have 3 plus 6u congruent to 1 mark A. Then I can subtract 3 from both sides. If I subtract 3, I have 6u congruent to negative 2 mark A. In general, we try to make this number positive, so I can add A here. We try to make this number positive. Add A here. I get 6u congruent to 6 mark A. Now be very, very careful. A very, very common mistake. People sometimes do this. Divide both sides by 6. U congruent to 1 mark A. That's wrong. That's wrong. There's no division rule. There's no division rule. Be very careful. There's no division rule. We cannot divide both sides by 6 here. That's wrong. That's wrong. Be very careful. Here we have 6u congruent to 6 mark A. This is a linear congruence. A, that's numbers, consider that's number A, B, M. This is A, this is B, this is M. Check GCD for A and M. GCD for A and M here is 2. And we know 2 divides 6. GCD for A and 6, for 6 and A. GCD for A and M is GCD of 6 and A, which is 2. And we know that 2 divides 6. 2 divides 6. So here I can divide all three numbers by 2. Divide all three numbers by 2. I have 3u congruent to 3 mod 4. Now the GCD between A and M now is 1. GCD between 3 and 4 is 1. Now I can find the inverse of 3 mod 4. Can we find some integer? Let times 3 plus integer times 4 let equal to 1. For 3 and 4 we can try -1 and +1 here. -1 times 3 plus +1 times 4 is 1. So the number in front of x is the inverse of 3. The number in front of 3 is the inverse of 3. So inverse of 3 congruent to -1 mod 4. Inverse of 3 congruent to -1 mod 4. If I and try to make this number positive in general, so I can add 4 here. Inverse of 3 congruent to 3 mod 4. Then I can multiply both sides by inverse of 3. Inverse of 3 congruent to 3 mod 4. On the left side, 3 times inverse of 3, that congruent to 1, so they get cancelled. We get u by itself. On the right side, 3 times 3 is 9. Then take 9 divided by 4, and find the remainder. 9 divided by 4, the remainder is 1. So u congruent to 1 mod 4. Then write it as an equation. That means u equal to 1 plus 4v, where v is an integer. Then I can substitute u here. Plug in this u here, then solve for x. If I substitute u, I have x equal to 243 plus 390 times u, where u is 1 plus 4v. If I simplify, I got 243 plus 390 plus 1560 v. Then combine like term, I get 633 plus 1560 v. So for the final answer, we can write x equal to 633 plus 1560 v. Where v is an integer. That's one way to write answer. Or I can write x congruent to 633 mod 1560. Either way is okay. We can write the answer as the equation or write it as a linear congruence. So we can write it as an equation or linear congruence. Either way is okay. Now, how do we check an answer? If we want to check an answer, this number 1560 here, 1560, it must be the least common multiple of these three numbers. This number 1560, it must be the least common multiple of these three numbers. And 633, it must be less than 1560. This number 633, it must be less than 1560. And if we plug in 633 to all three congruents here, they must satisfy all three conditions. So if I plug in 633 here, 633 divided by 8, remainder must be 1. 633 divided by 13, remainder must be 9. And 633 divided by 633 divided by 30, remainder must be 3. That's how we check the answer. This number 1560, it must be the least common multiple of these three numbers. And 633, it must be less than 1560. And if I plug this number into this linear congruence here, it must satisfy all three of them. That means 633 divided by 8, remainder is 1. Divided by 13, remainder is 9. Divided by 30, remainder is 3. That's how we check the answer.